Hi, my name is Brandon Gracely. I'm a high school math teacher. We're going to learn about the probabilities for independent and dependent events. And I'm going to change things a little bit this time. I have a bunch of pre-typed stuff that I'm going to talk about and point to. So if you're writing down notes, you can pause at the appropriate times to write some things down. So we're going to talk about compound events. So a compound event is a sequence of single events. When we learned about the fundamental counting principle, we had a series of stages. This is very much like that. One thing happens and then another thing happens and so on. A single event is independent if the outcome of prior single events in that compound event do not affect the probability of the event occurring. So let me just rephrase that. If you don't need to know exactly how a previous event happened to figure out the probability of this new event occurring, then it's independent. But if you need to know what did happen before, that's a dependent situation. I'm going to give you a couple examples in just a moment. So a single event is dependent if the outcome of prior single events in a compound event does affect the probability of the event occurring. So if you have to know exactly how the previous things occurred in order to know what the current probability is, that's dependent. It depends on what came before. And then just for a little bit of completeness for our language, a compound event is called independent if it has only independent events in it, but it's called dependent if it has at least one dependent single event inside of it. So let's look at an example. I got a little close on my cutting here. So imagine you roll a die twice, a regular D6 die with numbers 1 through 6. You roll it twice, and the event we're talking about is rolling an even number, then rolling an odd number. And you'll notice that together, because I'm doing two things in a row, I'm making up a compound event out of two single events. The first single event is rolling an even number. The second single event is rolling an odd number on the second die roll. So the probability of rolling an odd number on the second roll, that's the second part of our compound event, has nothing to do with the specific even number from the first roll. It's always a 50% chance, 3 out of 6, of rolling an odd number. It doesn't matter whether you rolled a 2 or a 4 or a 6, regardless of which even number was rolled first, you can calculate the probability of rolling an odd number second. And so the second roll, the fact that it's going to be odd, that's an independent event. And because the first event has nothing to depend upon before it, independent, independent, overall this whole thing is an independent compound event. Now let's look at a dependent event, and you'll notice there's more text here, and that's because these are more complicated. Dependent events are more challenging to work with, for sure. So for this event, suppose you're drawing 2 cards in a row from a shuffled deck, and that means you take out the first card but you don't put it back. The second card is only drawn from the remaining 51 cards. So what's the event? Let's look at the event drawing an ace and then a red card. Now you need to be a little bit familiar with how cards work, because some aces are red and some of them are black, and that's why this is a dependent situation. So first, it's a compound event, no problem here, because there are 2 things happening in a sequence. Can be more, 3, 4, 5, but in this case it's 2. But it's a compound event in which the probability of the second event, drawing a red card, depends on the specific outcome of the first event. You have to know which color of ace was drawn first. Some aces are black and some aces are red. So if you draw a red ace, there is a reduced probability of a red card being drawn second. There aren't as many left in the deck because you took one out. You took out a red ace, there aren't as many red cards. And if you compare that to when a black ace is drawn first, you've got a better chance at drawing a red card second. So here's the definition again. Because the probability of the second event depends on the specific outcome of the first event, then the second event is a dependent event, and we call the whole thing a dependent compound event. Now the confusion happens right here. We don't need to know, we do need to know which specific outcomes happened in the first event to calculate the probability of the second event. Now this is not a question of did we draw an ace or not. That's not what I mean. I mean which ace or which kind of ace did we draw first when we're doing these calculations. So let's come up with a rule for how to handle these. Now this is called the product rule for independent compound events. And you cannot use this with dependent compound events, although you can use the dependent one with the independent ones. We'll see in a minute. If two events A and B compose an independent compound event, that means that B does not depend on A. You don't have to know how A worked out to know how to calculate B. We have this formula. The probability that B and A both occur is the probability of A times the probability of B. And that's basically a lot like the fundamental counting principle that we learned in combinatorics. So you just multiply the two probabilities together, as long as you don't need to know which specific kind of A happened in order to figure out the probability of B. If the probability of B is kind of consistent regardless of which specific outcomes in this event were the ones that occurred. So that is for independent compound events only. In our example above, where we had to roll an even die and then an odd die, or roll an even value on the die and then an odd value on the die, there was a 3 in 6 chance of rolling an even number and then a 3 in 6 chance of rolling an odd number. And that's a half times a half, which comes out to 1/4 is the overall probability of rolling even then odd. So just multiply, that's all. So when we have dependent compound events, though, things are a lot more complicated. So if we have this A and B where B depends on A, the probability of B occurring depends on the outcome, the specific outcome of the first event A, then we have this formula. The probability of B and A is the probability of A times, now this is a bit unusual, probability of B given A. That's how we read that, or B given that A occurred. So this is called conditional probability. Now it can be that this number is actually impossible to calculate without breaking up A into smaller events that have sort of consistent destination probabilities for B. We're going to look at our example with the cards here in just a second. That to show this, we can divide up our first card draw into different categories. So we often will break A into smaller events, categories of outcomes, so that we can find those separate conditional probabilities. And that's just the same as we did when we were counting in cases in combinatorics. If we realized we couldn't use a single, so let's say, fundamental counting principle formula just once, we would use it multiple times on portions of our counting. We would organize our counting into separate little groups. The very same thing will happen here. We organize our little outcomes in the event A, the first event. We organize those into groups and we count based on those. So let's start talking about that card example again. We were drawing a red card after we drew an ace, and it would depend on which ace was drawn. So not whether we drew an ace, but which one. So let's call A the event that the ace is drawn first, and B is the event that a red card is drawn second. So we want to calculate ace, then red card. But the event B is a dependent event, so we want to use this kind of formula, but this value right here, we can't just know that. We can't know it in a single calculation because it's complicated. It depends on which part of A actually occurred, which specific events occurred. We can't calculate it directly. We break A into smaller events in which the probability of B occurring is consistent for each outcome in that first event. So we look for a way to divide it up so that we can calculate the probability of B. So I'm going to make two little subsets. That's what this symbol is here. Let C be a subset of A. It's an event that the black card, a black ace, is drawn first. And we have another event, D, also a subset of A, the event that a red ace is drawn first. Together, these make up all of A. Right? If we take the black aces, that's C, the red aces, that's D. Together, it's all the aces. So we've subdivided or divided up A into smaller events or subsets. Now the probability of drawing a black ace is P of C, that's the black ace. There are 2 black aces out of 52 cards, that's 1 in 26. Now here's the part that really matters, so pay close attention. If the black ace is drawn first, the probability of drawing a red card is the probability of drawing a red card given that a black ace was drawn first, B given C. That's 26 out of 51. There are 26 red cards left out of 51 cards. A black card was drawn first, so all of the red cards are still there, all 26 of them. So that's the probability for B, given that we only took out a black ace to begin with. Now for red aces, that's this next line here, that's P of D. D is the red ace event. Also 1 out of 26. That's interesting. Those are the same number. Doesn't matter at all. But here's the part where it's different. If the red ace is drawn first, the probability of drawing a red card second is the probability of red card given a red ace was drawn, only 25 out of 51. So see the difference here and here. That's the difference. Notice it's probability of event B occurring, but it's different for the two different circumstances, depending on which specific outcomes happened first. This is if a black ace was drawn, this is if a red ace was drawn, a reduced probability of getting another red card. So overall, we end up with this. The probability of A and B both occurring, I'm sorry about my formatting here, probability of A and B both occurring is, now this part is the regular conditional probability formula with C and D. And just like in combinatorics, it was just divided up into two cases with a plus sign in between. The C one is here, 1 out of 26 times 26 out of 51. That's right there. Those 26s will divide out and you get 1 out of 51 for this. Sorry, this is the final calculation down here. And then here we have 1 out of 26 times 25 out of 51. That's a terrible number. And then when you add them together, you get this sweet 1 out of 26 is the overall probability. Okay, so keeping track of all that is really challenging, and so I'm going to show you how to use tree diagrams to organize all of those different pathways, all of the different categories of events, and then you can use the tree to actually calculate the probabilities directly. So this is a pretty cool trick. What I'm going to do is first let's return to that independent example first. Call this the independent tree diagram. And that was the one with the dice rolling. Remember, we rolled an even, then we rolled an odd number, and we were looking at the probabilities that that happened. It worked out to 1/4. Well, let's draw a tree to see how it all works out. The first thing that can happen is you can roll an even number or an odd number first. Now, rolling an even number, that was A. So I'm just writing the event A there. And then rolling an odd number, now this is rolling the first time, is A prime. I want to point out it's not B. B is rolling the second in the second stage here. So it's not like A is even and B is odd. A is even and first. B is odd and second. So be careful about that. They're not the same thing. And maybe we'll just continue and do the next layer here, the next stage. We can roll an odd number now, that's B, or not an odd number, an even number, that's B prime, or not B, you can say. And then, you know what, actually, if we roll an odd number first, I don't even care what happens. We aren't going to be calculating this. We want to know what happens when you go roll an even number first, and then an odd number second. We're going to calculate that probability. We don't care about the rest of the tree, really. But I'm going to show you the structure of it a bit. Now, this first line here, this branch, we're going to call that the probability, we're going to label it, I'm sorry, with the probability of following that branch. That would be 3 out of 6, or 1/2. The chance of rolling an even number is 3/6. The chance of rolling an odd number is also 3/6. So I'm going to label both of those branches. And maybe I'll just, let's see, grab a color here. This number here, this is P of A, the probability of following A, or that A occurs. Now over here, what's the probability of B occurring given that A did occur? Now this is an independent event, so it actually doesn't matter how A occurred. We just know that it did. And so this number here, 3/6 or 1/2, is the probability of B given that A occurred. And it's always just going to be 3/6. It doesn't matter which specific outcome happened. And then this one down here is also 3/6, the chance of getting an even number second. And you'll notice that 3/6 and 3/6 is 6/6 or 1, and the same thing is true down here. And if I was to put a number on this branch right here, it would be 1 or 6 out of 6, something like that. Now to follow these two branches, you have a 3 in 6 chance of following this branch, and then a 3 in 6 chance of following this branch. Together we get this. The probability of A and B both occurring is the probability of A times the probability of B, or we can write the probability of B given A, which is 3/6 times 3/6, which works out to be 1/4 or 25%. Okay, let's look at our second example, the one where we have an ace and then a red card, and this one is dependent. So the first thing that can happen is we can draw an ace or not draw an ace. So I'm going to first draw the not an ace branch here. That would be A prime. We said drawing an ace was called A. Now the trouble is we can't just draw an A branch here because we need to divide it up into our two little groups. One of those groups was called C and one of those groups was called D. And I think we said C was the black ace first, right? And D was the red ace. I'll write the word ace there. And this is not an ace. And we're not going to care about this branch, although I will label it. The probability of drawing something other than an ace is 48 out of 52. Now these two each are 2 out of 52. You'll notice that those three numbers add up to 52 out of 52, which is 1, and that's always true. When branches radiate from a single point like this, they have to always add up to 100% or 1. Now if we follow the black ace first branch, then we can draw a red card or a black card. Those are the choices. The red card is called event B, and the black card would be B prime or not B. So this is a red card, and this would be a black card. Now, because we drew a black ace to begin with along this pathway, the probability of drawing a red card is 26 out of 51 now. That number goes down by 1 because there's one fewer card in the deck. 26 of them are still red though. This number down here is only 25 out of 51 because a black card is now missing. So I'm just going to draw on here that this branch followed by this branch achieves our goal of getting an ace and then a red card. And we're going to have that happen in another place down here. For if we follow this branch, getting a red ace first, then we can still get a red card that's not that first ace that we drew, or we could get something else. The probability of getting this red card second, out of 51 cards, only 25 of them now are red because one of them was used up in this ace. 26 of them are black, which would follow that path, the one we don't need. So following, maybe I'll grab a different color for the second branching here. We could go this way here and then here to get that result. Now this probability here plus this probability up here, those ones are going to give us the final result. So this one is the probability of C and B both occurring. So drawing a black ace and a red card. That's the probability of C times the probability of B given that C occurred. Now that's that number right there. Let me label that. This is the probability of B given that C specifically occurred, that we drew a black ace. And you'll notice how that's different from the number down here. So that's 2 out of 52 times 26 out of 51, and that's going to work out to that 1 out of 51 I was mentioning earlier. Now the other one here, that is the probability of B occurring given that D occurred first, or that a red ace was the first card drawn. So the probability of D and B occurring, so together that's all of A, probability of D, times the probability of B, given that D is what happened. Still 2 out of 52 to begin with, but the second number here is 25 out of 51, a reduced probability of drawing a red card, since D used up a red card. And that gives us kind of a surprising number, 25 out of 1326. Now together, we get the total, the probability of A and B, you get by adding these two sort of cases together. Did we get this kind, or did we get this kind? Together, those give us all of the different variations, and this is our final number, 1 out of 26. Okay, let's do a few practice questions together. Jim has a 75% chance of hitting his first free throw in a basketball game. If he misses the first shot, he has a 30% chance of hitting his second free throw, but if he makes his first shot, then he gets an 80% chance of making his second free throw. So he gets a little rattled if he doesn't hit the first one. So let's draw a tree diagram to show the possible outcomes and the probability for each outcome. So I'm going to kind of move this up a little bit and try to fit everything kind of small on here. So he's got to hit that first free throw or not hit the first three. Hit it. I'm going to say so yes or no. Yes, he hits it. No, he didn't. He has a 75% chance of hitting this one. That means he's got a 25% chance of not hitting it, and those add up to 100%. They always have to when they radiate out from a single point. Now let's go to his second free throw. If he misses the first shot, he has a 30% chance of hitting his second free throw. So miss followed by a hit, so that's a yes, that's a 30% chance. Now the alternative is that he does not hit it, which then would be a 70% chance. 100% minus 30% leaves 70 for the other branch. If he makes the first shot, he has an 80% chance of making his second free throw. So that's up here, 80%, and down here then, 20% to the no path. Now, we've got our tree diagram that shows all the possible outcomes and the probability for, it doesn't show the probability for each outcome yet, only for the kind of outcomes in the middle. We now need to calculate sort of the end here for each one. What's the probability basically of him making the first two free throws in a row? That would be 75% times 80%. Now that's going to work out to 60%. I'm going to grab a calculator to show you a couple ways to do that. Apologies for the big scratch on my calculator. See if I can tilt this so you can see it well. So I like to use decimals when I do this. 0.75 times 0.8, 0.80. Now my calculator gives me fractional answers, 3/5, but I can convert them with this button here to a decimal answer, 0.6 or 60%. It's difficult to do like 75 times 80. You get this big number and you got to know how to handle it. An alternative is to use fractions, 75 over 100 times 80 over 100. Those are your percentages. And that's, once again, gives you a fraction 3/5. On here I convert that to 0.6 or 60%. Okay, let's try this one. 75% times 20%. Now I know that 75% of the time he makes the first free throw and then this other stuff happens. Well, 60% out of the 75 is used up. This is going to work out to be 15%, so I get a total of 75 along this branch. The remaining 25 are going to be down here. But I can multiply and just double check. 75% times 20%, so 0.75 times 0.2, looks like 3 out of 20, or 0.15, 15%. Let's continue down here. This is 25% times 30. And if you can just do the math, that's a quarter of 30. So half of 30 is 15. A quarter of it will be 7.5%. And now this is going to be 25% times 70%, which is the remaining bit that makes up 25 after this is gone. So it looks like 17.5 to me. And those numbers all add up to 100%, as they must every single time. Okay, that's the first example. Okay, we've got a manufacturing process that produces pencil sharpeners with a 1.3% defect rate. So 1.3% of all of the sharpeners are defective. The quality control process detects 60% of defective products before they're shipped to stores. Two questions. What percentage of all defective sharpeners are shipped to stores? And then what percentage of all sharpeners are defective? Now I'm going to draw a tree again to help make sense of this. So the first kind of question or thing that can happen is we can have something that is defective or that's not defective. Let's just call it good. And we know that there's a 1.3% chance of any one pencil sharpener being defective. Subtracting that from 100, I get 98.7% of them are good. Now if it's defective, it can be noticed by the, or detected by the quality control process. I'm going to call that sort of found or not found. So what's the percentage? 60% of the defective products are noticed or detected. So this is 60% of the time, and this then is 40% of the time, so they add up to 100. So what percentage of all defective sharpeners are shipped to stores? So if a sharpener is defective, what is the chance that it goes to stores? That's 40%. That's just this number, no calculation required other than, I guess we subtracted from 100. That's the probability of a defective sharpener being shipped to store. So that's the percentage of sharpeners that are shipped to stores as well. Probability and the percentage shipped are the same here. What percentage of all sharpeners shipped are defective? Okay, we're talking about something that is defective and is not found. So that gets shipped to stores. Okay, so we're going to need a little bit more than that. So let's just finish off the whole tree here. So this is defective sharpeners that are found. So we have 1.3% times 60% is, so that's 0.013 times 0.6. Oh, 0.0078. Does that make sense? Yeah, a little bit less than 1%. And this one here will be 1.3% times 40%, which is going to be 0.0052. Together those should add up to 0.013, and they do, so that's fine. Writing these as decimals, not percentages right now. And then this, nothing to worry about, we just kind of carry this through. This would be 0.987. Now this is a little bit of a complicated question. What percentage of all sharpeners shipped are defective? Now these ones here are not shipped. Those are the ones that are not shipped, which means that the percentage of sharpeners shipped in total is the sum of these two numbers here, and then the portion that is defective is just this part. So we're going to write this, the percentage of shipped sharpeners that are defective is, now we take the percentage of defective ones overall, and we have to divide by not this number here, but the sum of these two. How many sharpeners are sent? This percentage of all sharpeners is sent. So very subtly different. It's not quite 0.52%. It's actually a little bit higher than that. So once we divide, so 0.0052 divided by, I'm going to use brackets now, 0.987 plus 0.0052. I'm going to get a decimal here. So 0.0052 0.00524. So, yeah, that's right, approximately. Sorry, I should show you there. That's 5.24 times 10 to the negative 3. And I can write that as 0.524%, if that's easier. So about 0.5% of sharpeners are shipped that are defective. Okay, suppose we have a new medical test, we're going to call it test A, that places an LED light and a sensor on a person's skin to test for a type of infection. And the existing test, we're calling it B, it uses a blood sample, but it takes longer and it costs more to complete. But test A is accurate only 75% of the time, where test B is accurate 92% of the time. Let's draw a tree diagram to show the possible outcomes of using both tests and the probabilities for each outcome. Okay, so let's start with, I'm going to maybe put some labels at the top here. We can have test A and then test B are going to be sort of columns in our tree. Let me just move up a smidge here. So test A can be, let's say, correct or incorrect, so accurate or not, like this. There's the branching two choices that we have. Test A is correct 75% of the time, which means it's incorrect 25% of the time. Now test B, if test A is correct, B can be correct or incorrect. And if test A is correct, what's the probability of test B being correct? Well, actually, it's always just 92%. It doesn't depend on which of these branches we followed first, which that leaves 8% down here. So the second portion of this diagram, correct and incorrect down here, we get the same numbers here and here. You don't need to know how test A worked out to be able to figure out the probabilities for test B. This is an independent situation. There's no relationship between test A and test B's specific outcomes. So let's find the probabilities of each outcome. So what's the probability of following each of these paths? This would be 0.75 times 0.92. So that's 0.69 or 69%. This would be 0.75 times 0.08. Now it's going to add up to 75%. That makes this 0.06. I don't even need to calculate it. Down here, 25% of 92. And that's going to work out to 0.23. I better just double check that. That was in my head. 23%. And then last we have 25% of 8%, which will work out to 0.02. The whole thing works out to 100%. So those are the probabilities. For example, what's the probability that both tests are accurate? 69%. Okay, let's look at one last example. Again, with a medical test. A medical test, a single test for a common virus, has an 8% false positive rate and a 3% false negative rate. A false positive means that 8% of the time when somebody doesn't have the virus, it says that they do. And that's an incorrect result in one direction. And a false negative is 3% of the time it will say that a person does not have the virus when they do have the virus. So false positive and false negative. If the overall incidence of the virus in the population is 23%, we're going to need that in a minute, what is the overall accuracy of the test? So we're going to draw a tree, and the first kind of branch here is the person infected or not? And so there's a 23% chance of any one individual being infected, and subtracting that means there's a 77% chance of a person not being infected. Now, if the person is infected, then either we can get an accurate result or they're infected. So what would be the wrong result? That would be a false negative. It should say that they are sick, but it says that they're not. Now there's a 3% chance of that happening, 3% false negative rate. So that means there's a 97% chance that an infected person is accurately going to be evaluated as saying yes, that they have the virus. Now down here, a not infected person could be accurately assessed, and that would mean that it says that they are negative. The opposite would be a false positive, where it positively identifies them as having the virus, but they should not be identified that way. False positive happens 8% of the time. And so that makes this 92%. Okay, so let's see the overall probability for each of these scenarios. So I'm going to multiply 0.23 times 0.97. This will be 0.23 times 0.03, that's 3%, don't forget the 0 there. 0.77 times 0.92, and 0.77 times 0.08. So I'll just multiply all those right now. Okay, so we have all of our probabilities, and notice that we really had to know the percentage, or have an estimate for the percentage of the population that was infected. Otherwise, you can't know how often false negatives and false positives are going to happen overall. So the kind of total error rate, if you like, this is the inaccurate test in one form, and this is an inaccurate test in another form. And by adding those two things together, what do we get? 6.85%. So the overall accuracy, so maybe I'll just write it down here. So the overall accuracy is, I'm going to add up the other numbers actually, 0.2231 plus 0.7084. Those are the ones that are accurate results. And that's going to be 0.9, what have I got, 93 something? I'm going to grab this just in case, folks. $9,315, okay. .15% accuracy. Now, if we had a different situation where the rate of infection was lower and this number then was higher, we would end up with more false positives, and so that would change the overall accuracy. So the accuracy depends on how widespread the virus is. Okay, thanks.